So in this question 8, the sizes are given. The ionic radii for lithium is 0.074. For calcium is 0.1, oxygen is 0.14, sulfur is 0.185, fluorine is 0.13, and chlorine is 0.18. Which of the following compound has the most exothermic lattice energy? So the most exothermic, the one in which the ions are closer to each other and the charge is greater as possible. So what could be the answer? For to have a higher lattice energy, the size should be small as possible, size of the ions, and the charge should be greater. So what could be the answer here? Which one you think will have high lattice energy or more exothermic lattice energy? A, B, C, or D? The sizes are given. The charges on the ions are also shown or given. So first for lithium chloride and lithium fluoride and lithium chloride, you cannot, because they are having plus charge only. So you are left with calcium oxide and calcium sulfide, because both of them have charge plus. Calcium oxide, so calcium is there and oxygen, and calcium sulfide, calcium +2 and sulfur -2. So the charge is same. Now when you compare the size, so calcium is same for both, so we'll only compare oxygen and sulfur. So we'll check their size. You can see oxygen size is smaller as compared to sulfur. So it shows that in this calcium oxide, the ions will be closer. So the higher lattice energy is for calcium oxide. Is it clear? Yes, is it clear? Any doubt in this part? Like why the calcium oxide is having a higher lattice energy or more exothermic lattice energy? Because its size of the ions is smaller and they have the greater charge. So when we compare the charge, C and D both have the same charge, like calcium +2, oxygen -2, calcium +2, sulfur -2. But the size is smaller. As the size is smaller, the ions will be closer. That's why higher lattice energy. Yeah, is it clear, this part? The calcium oxide, why it's having the higher lattice energy or more exothermic lattice energy. What about A and B? When you compare A and B, lithium fluoride, so lithium plus charge, fluorine minus. Lithium chloride. So to have a higher lattice energy, what should be what is the criteria? The charge should be greater and the size of the ions should be smaller. So when you compare lithium, so when you have lithium fluoride, lithium chloride, calcium oxide, and calcium sulfide. So as you can see, the charge is greater in calcium oxide and calcium sulfide as compared to lithium fluoride or lithium chloride. So they cannot be answered because they don't have a greater charge. To have a higher lattice energy, charge should be greater and the size should be smaller. So calcium oxide and calcium sulfide is having a greater charge. Then when you compare the size, the ions should be closer to each other to have a higher lattice energy. So you found that oxygen is smaller in size as compared to sulfur. That's why calcium oxide is having the higher lattice energy. So A and B cannot be answered because they don't have greater charge. It should have a greater charge and smaller size. Then the next part, which of the following will show a greatest difference between the experimental lattice energy and the ionic model? So the difference depends on number one, the difference between the lattice and the theoretical value depends on size of positive ion, mainly the charge. The charge of the positive ion should be greater and the size of negative ion should be larger, so that it will have greater difference, to have a greater difference between theoretical and practical value. So which one you think will have a greater difference in the theoretical and the practical value? The charge of the positive ion should be greater and the size of the negative ion should be greater, so that they have a greater difference between the theoretical and the practical value of the lattice energy. So what could be the answer here? A, B, C, or D? Yeah, D is the right answer because sulfur is having a greater size. So when you have calcium oxide and you have calcium sulfide. So because the calcium ion is same for both, so here we have sulfur and oxygen. So sulfur larger size, so distortion, greater distortion or attraction towards the positive. That's why greater lattice energy of calcium oxide will be higher, but this will have a greater difference in the theoretical and the practical lattice energy. So briefly describe an experiment with a diagram of apparatus you could use to show that oppositely charged ions such as copper 2 chromate, and describe what you would you expect to see. So just now we discussed this. This is the same experimental part. So we can have a U-shaped tube and we will observe the migration of the yellow ions towards the negative positive electrode and blue ions towards the negative electrode. So this is the same thing we discussed. So the same figure you can draw, copper to chromate, and show the migration of the ions and what you will observe. It's the same question. The ions in ionic lattice are held together by overall a force of attraction. Describe the force of attraction in ionic lattice. So how we describe this force of attraction in ionic lattice? The force of attraction between the oppositely or positive and negative charge. So electrostatic force, basically they asked what is the meaning of electrostatic force. So what's the meaning of force of attraction? And so the electrostatic force between positive and negative charges suggests two forces of repulsion which exist in the ionic lattice. Because ionic lattice, it's a regular arrangement of the ion. So we have positive and negative ions. So there is attraction is there, electrostatic attraction is there between the positive ion and the negative ion. But in the question they are asking, there are give two forces of repulsion which exist in ionic lattice. So what are those forces of repulsion which exist in ionic lattice? As we know, like charges repel each other. So there is a repulsion between the negative ions, two negative ions, and there is a repulsion between the two positive ions. So the two forces of repulsion which exist, the repulsion between the positive ions, like this positive ion and positive ion repelling each other, and repulsion between the negative ions. What is the electron density map? Electron density map, when we represent the structure, the distribution of electrons in the ions, we call that electron density map. So example, as we know, sodium chloride. So sodium tend to lose electron, and non-metal chlorine tend to gain electron. But what is electron density map? Electron density map, it's not the shells. It shows the probability of finding electron, or the region of finding electron is maximum. So when we represent the electron density map for sodium, we'll draw circular these lines to show the electron density of sodium, and these are not the shells. If the lines are closer, it means greater electron density, like we have greater probability of finding electron. If the distance between the lines is increasing, it means probability of finding electron decreases. So for ionic compound, we use a separate electron density maps for positive ion and negative ion. So the question is, which of the statement is evidence of existence of ions in ionic compound? So which of them is existence of ions in ionic compound, and how we work out this electron density map? We pass the X-ray. So when we pass the X-ray through this, we get an image of the ions, and that image of the ions is simply known as electron density map. So what could be the answer here? How we can? So for question number 11, ionic compound in a solid state conduct electricity. That's wrong. When any ionic compound in solution is electrolyzed, the migration of ion can be seen. It is not always true, because some of the ions are colorless, so we don't observe their migration. So that's not always true. In electron density maps, ionic compound, there is no single line representing the electron density. surrounding both cation and anion. So as you can see, like the positive ion is there. What's the meaning of statement C? You have positive ions and we have negative ions. So when we represent this electron density, the region where probability of finding electron maximum, like this is for positive ion, this one is for negative ion. So what it shows, you can see there is no, what is the meaning of this statement? In electron density map for ionic compound, there is no single line representing electron density that surround both cation and anion. You don't find any line which is going around both cation and anion. You don't find this line. So which statement? So this is a true statement. There is no single line representing in electron density map of ionic compound. There is no single line representing electron density that surround both cation and anion. So that's true. C is right. In electron density map of ionic compound, there are some single lines representing. So that's wrong. So the right answer statement is C. Is it clear? This question 11. The region or the probability of finding electron, where the region where we can find electron easily, we call that region as electron density. So for positive ion and negative ion, their electron density maps does not coincide with each other or combine with each other. So we can say that there is no single line which is around both positive and negative ion. Positive ion have its own electron density, negative ion is having its own electron density. There is no line which is just combining both of them together. Is it clear, this part? The question is about the lithium iodide. So you can draw a dot and cross diagram for this. Lithium will lose electron. So in the outermost shell, because lithium is atomic number 3. So when it loses electron from the last shell, it will have only 2 electron in the inner shell, the first shell. And iodide, only the outer shell we have to draw. So all the electron in lithium, but for iodine, only the last. And dot and cross diagram for lithium iodide. In the next question, the experimental lattice energy of lithium iodide and the theoretical lattice energy is different. So experimental and theoretical lattice energies are not same, or so will the experimental lattice energy is more negative or less negative? Experimental lattice energy is always more negative or always higher for any kind of compound. So what's the reason for that? Because the same reason, when theoretically we assume ions are perfect spheres, this is our assumption, but in practical ions are not perfect spheres. The polarization of ions occur. So experimental lattice energy is always higher than theoretical lattice energy. And reason is because of distortion or polarization. An iodide ion is larger in size, so it will have greater polarization. So why there's a first thing, why 3 marks? Number 1, we'll mention experimental lattice energy. will be higher than theoretical. What's the reason? Because distortion or polarization of the ions occur. So ions will come closer to each other. This will result in higher lattice energy. State and explain. The higher means more negative. When I say higher, it means more, because magnitude is important, negative sign. Like when I say in a number line, when we say in terms of number, when I say 700, minus 700 and minus 800, in terms of numbers, minus 700 is higher value as compared to minus 800. That is in terms of number, like on a number line. But when I say in terms of lattice energy, so 800 minus 700 is a smaller value as compared to minus 800, because negative sign here shows both are exothermic and magnitude is higher. It means greater lattice energy. So when ions distortion occur, the ions will come closer to each other. So as ions will come closer to each other, result in a so theoretically, we assume ions are perfect sphere, but practically they are not perfect spheres. So they have distortion. If two negative ions are in same in size, but practically what happens, the distortion, so ions come closer to each other. So if this was the theoretical value was minus 700, then the practical value will be minus 800. Means the higher negative value. Negative sign shows it's exothermic, and 800 is showing the magnitude of energy which is released. State and explain how electron affinity value as you go down the group from chlorine to iodine. What happened? So as we go, electron affinity means when electron is added to a neutral gaseous atom. That's called electron affinity. So what happened? Fluorine is smaller in size as compared to chlorine. Chlorine is smaller in size compared to bromine. Bromine is smaller in size as compared to iodine. So you can see that fluorine is smaller in size, so attraction of the electron is much greater. So it can easily attract electron, and as it can easily attract electrons, so what we will observe, we'll observe fluorine will have a higher electron affinity. So as we go down the group, the electron affinity become less negative, like this will release more energy. And this will release less energy when electron is added to this iodine. What's the reason for that? Because electron is further from the nucleus for iodine. Or you can also mention there's a greater shielding effect. Like because iodine is having more shells, so greater shell, more inner shell electrons, so more greater shielding effect. So it does not experience the same force what is experienced by electron in fluorine. That's why fluorine affinity will be higher as compared to iodine. So as we go down the group, you'll mention electron affinity become less negative, or it will decrease as we go down the value. And reason for that, because electron is added further from the nucleus, or there's a greater shielding effect. That's why less exothermic. Is it clear? This part? So because electron is added to the shell, which is further away from the nucleus, or more shielding effect. In iodine. The lattice energy can be calculated by electrostatic theory and a Born. What can you deduce? The fact that experimental values are very close. So what you can deduce from this, if the value, the experimental value, for example, if the experimental value is say minus 200 and the theoretical value is minus 198. So they are very close to each other. What this gives an idea, if the two values are closer to each other, so this shows that this is 100% ionic, that the bonding is 100% ionic and no polarization occur. So bonding is 100% ionic and there is no polarization occur. That's why the theoretical lattice energy and the practical lattice energies are same. Which of the following result is the most polarizing cation? Like in which case the cation will be more polarized, or we'll have greater difference in the theoretical and the practical lattice energy. So size of the cation, the positive ion should be smaller and charge on the cation should be greater, the positive ion. So B is the right answer. Which of the following ion has the smallest radius? Which one you think will have the smallest radius? Yes, so for question 16, what could be the answer? So best way to work out this, compare the number of proton and electron and the number of the shells occupied. Fluorine is having 9 protons and 10 electrons because it's an ion. Magnesium is having 12 protons and 10 electrons. Sodium is having 11 protons and 10 electrons. All are isoelectronic. This is having 8 protons, atomic number 8, and 10 electrons. So which one will have a greater attraction to if they are isoelectronic means they will have the same size of the same number of the shells, but you can see the same number of the shells, same number of electron, but pulled by 12 protons. So greater attraction towards the nucleus. That's why it will be smaller in size. So B is a correct answer. Ions with the same electronic structure are known as isoelectronic. Which of the following compound is made up of isoelectronic? Isoelectronic means contain the same number of electrons. Yes, C is the right answer because sodium, when it take sodium is 11, but when it loses, it will have 10 electrons. Oxygen take it's 8 electrons, but it took 2, so it will be 10 electrons as well. Calcium and oxygen cannot be because calcium is atomic number is 20, so there are 20 electrons initially, but when it loses, it will have 18. But oxygen is having 8 electron, it gained 2, so it will have 10 electrons. So they are not isoelectronic. C is the right answer. Question 20. What could be the answer for question 20A? Which diagram shows the trend in ionic radii for the 4th sequence? The diagram are not to scale, like you don't have to stay the magnitude. Which diagram shows a trend in ionic radii for a sequence lithium, sodium, potassium, rubidium? Means we are going down the group. Which graph is correct if we are going down the group? From lithium, sodium, potassium, and rubidium. What happened to ionic radii as we go down the group? The size of the ions or size of the atoms? A is the right answer because there are more electron shells. That's why size increases. The next part, which diagram shows a trend in ionic radii of a sequence sodium, magnesium, aluminum, and silicon? You can see all, so sodium, magnesium, aluminum, and silicon. So sodium, magnesium, aluminum, silicon. Sodium, 11 protons are there atomic, but there are 10 electrons. They are all isoelectronic. 12 protons are there and 10 electrons. 13 protons are there, 10 electrons. 14 protons are there, 10 electrons. Which sequence shows their size as we move from lithium, magnesium? So which graph shows their size? Because more protons, less electrons, so size decreases. Yeah, D is the right answer. Some of energy changes are involved. Electron affinity. Electron affinity means when electron is added, A is electron affinity, B is lattice energy, C is atomization, and D is formation. Which enthalpy change is represented in P? When ions, we form an atom in a gaseous state. What we call this? A, B, C, or D? When we form an atom in a gaseous state, what we call this? So when atom is formed in a gaseous state from its element, we call